I don't know how many of you are interested to listen about technically about the LDMOS amplifiers. Okay, one is enough. So the Power Genius is, let's say, I will proudly say that this is the best amplifier on the market. So it's truly SO2R. Now we have new version which is 3-way. It's not. It's one radio, 3 antennas. So it's the 3-way. It's broadcast quality build, and we really put attention on each and every detail when we design the Power Genius. So what I want to say, what is specific for this amplifier, is that everything inside is almost software defined. So in our production, we are not using screwdriver for any kind of tuning. So everything is done by software. So when we have sub-modules like RF modules, the RF modules goes on the test bench. Software is calibrating RF module and on the triggers for the protection and everything. Same with filter box and same with amplifier when it is assembled. So filter boxes are tested each band 7 minutes key down on the full power. So it means that before we assemble filter box into the Power Genius, it goes hot for 76 hours and a half. And then on the test bench, when everything is assembled and motherboard calibrated and everything, it goes on the final calibration. And at the end, we have everything stored in the software, so we can recall, check the data and the history of every unit. Once when everything is done, the last test is half of hour, full power on the load 3-to-1. And after this test, it goes to the cosmetic check and packing and shipping. So, but I will now try to explain you as simple as possible some of technical interesting things about the LDMOS amplifiers. It is the Power Genius XL. We have very smart motherboard. Hardware-wise, it's measuring instruments. Module, we have bias is very smart. It's controlled from motherboard. And we have a very rigid and very efficient protection. So when we are talking about the protection of LDMOS, we have couple of things we have to take care about the LDMOS. They are very rigid, but they are very sensitive on some of circumstances. So as you can see, before the filter box, we have one RF probe which is taking care to control SWR between the amplifier and the input of filter box. So what can happen, and it happens, so you can have a failure in filter box, and then this failure is not sensed by usually oriented directional coupler at the output. So because the problem in filter is after this directional coupler, which is measuring SWR on the antenna. And when you see the amplifier with one directional coupler, just forget it. So the protection of this amplifier is zero, absolutely zero. Because it cannot protect amplifier if the damage of component is in a filter, because this probe doesn't see it. So this probe will, of course, control it, and this protection is in a time frame of 1 microsecond. Later on, I will explain why. This one doesn't have to be that fast. it is measuring SWR and taking care if SWR is going into the foldback area, like from 2 to 3, then the amplifier will decrease the power, and it can happen in tenth of milliseconds without the problem, because it's not a big deal for transistor. But this one is essential. Without that kind of protection, any amplifier is very weak. So when you are choosing your amplifier, these things are to be considered seriously. Then, I want to comment one common mistake from the guys when they are discussing or developing amplifiers. And I can see plenty of homebrew amplifiers and projects of amplifier of 1.5 kilowatt, for example, with transformer 1 to 3 or 1 to 9 when we are talking about the current ratio. So, this is the principle. We have a push-pull, we have drain voltage, and here we have RMS voltage generated, which is twice DC. So if it is 50 volt, we have 100 volts, twice it is push-pull, and then we multiply with 0.7 for RMS, and we have RMS generated on the transformer, 9 to 1. So this is, so output power, so actually we have output volt RMS with turn ratio, which is now 3. If we here have 70 volts, 100 volts in total, multiply 0.7, it's 70 volts, multiply by 3 at the end of the transformer, we have 210 volts, and then output power will be calculated simply as square of this generated voltage here, which is 210 volts squared, and then divided with output impedance, which is 50 ohm. So it is the basic principle. There are some variational. Okay, and this is, we can come back on this is transformer of Power Genius, and it is interesting table. So now you can see, if you have if you have transformer 1 to 3, and then you read that guy has 48 or 50 volts. So theoretically, he can generate 829 watts. So to have 1500 watts, you have to have device on 65 volts. And you have many of those home brews which are 1.2 or even claim 1.5, which cannot be true. It can in some cases, I will explain later. So without transformer 1 to 4, so you cannot have, with the typical 50 volt devices, you cannot have, with 1 to 3, you cannot have, you need to have 1 to 4 to have 1.5 kilowatt. So we have 52 volts, Power Genius is 52 volts, so, and we are running 1750, so we are in this range. So now 2K5 from Ampleon, the latest device, which is on 75 volts, you can gain from 2 of those, you can have 3.6 kilowatts because it is 75 volts. So this is just a very clear explanation of mistakes you can find very often daily on the Facebook or AM radio dedicated social medias. Okay, so here we are. You can see the output transformer in Power Genius. Then the ferrite selection. The ferrite selection. What I want to point out is that, like in any development almost of anything RF dedicated, any device, everything is about the compromise. So we don't have any straight line and that's it. No, everything is compromised. And you have to understand a couple of things. to choose and to make compromise which satisfied you. So one of these compromises are ferrites. So this is enough, so I don't want to go into the ferrites deeply, they are very complex. So wrong ferrite choice, it will just make project not possible to be executed, or too much permeability or too low or whatever. So, and then broadband of the transformer. I will come later and I will explain you the broadband, how broadband transformer has to be for LDMOS amplifier, not as the many people are thinking. Output filter. So output filter of LDMOS amplifier is maybe the crucial sub-module in the amplifier. Maybe the most important. It matches your antenna on the LDMOS, which is very important, and also it take care, it can be solving of your problem or generator of your problem. So we have two type of filters. We are using diplexers from the very early, so we never lose the low pass filters. I will explain why. So the low pass filter, by its nature, it is just passing the carrier and just blocking the harmonics. And okay, now you have transistor, you have carrier going on the antenna, running, door is open, and then you have harmonics, door is closed, and what they are doing, they will come back on the LDMOS. Level of harmonics in push-pull, third harmonic is less than 10 dBs lower. So we have maybe 12–13% of output power in a third harmonic. Plus you have some power in second or the other harmonics in the line. So then you have a lot of power. You have 1 kilowatt, and then you have 150–200 watts of harmonic power coming back on the transistors. And then it is how the mess begins. So these harmonics, uncontrolled harmonics, are killer of LDMOS. Simply. So you cannot do this. So with high pass, with the diplexer, we have low pass filter for carrier, so the door is open. But we open another door in the high pass filter, so the harmonics, gentlemen, it is your way. So their way is ending on 50 ohm terminator resistor here. So the harmonics are just going into the high pass filter and transferring into the heat on 50 ohm resistor. And then transistor is breathing, it doesn't receive any energy back, so everything is going in the proper way. And it is how it looks like. So why the low pass filters are killers of LDMOS? Because those harmonics, those harmonics, these are peaks generated with carrier and harmonics, and they are not controllable. So the shape, the value of these peaks depends on the phase of these harmonics, and you are not controlling this at all. So the phase depends on the reactance of your antenna. So when you have 50 ohm in our laboratory, we put dummy low. Ola, 1, 2. Is it my mistake or Ola 1? 1. Battery, okay. Doesn't matter. So the looks, sometimes with good phase, but without the control, it can help. But in most of the cases, the phase will be in a way that you will have peaks, and peaks are killing LDMOSes. And it means that your good amplifier work, I don't know, 2-3 years without a problem on very good antenna, then you change antenna and it blow up. It is expecting. So another advice, when you are buying LDMOS amplifier, take a look, don't buy any with a low pass filter, except if the LDMOSes are working on the much lower voltage than they are declared. Okay, here we are. Okay, and now it is how it looks like. This is low pass filter, and you can see this is a plot of high pass filter, or duplexer filter. So, and you don't have it. So then everything is under the control, because regardless of the impedance of antenna, you don't have harmonics, and your amplifier is working in a controlled condition. So we know what is going on, and we know that we don't have any circumstances which we cannot make amplifier, or it's not good way to make amplifier which depends on something we are not controlling, and we know that there are some circumstances that are not healthy for amplifiers. So it's just guessing and not a good path for making developing a good brand. So more of course, duplexer filter effectively eliminates IMD contribution from higher order harmonics, because they are also decreasing the IMD of the amplifier. And it is in principle how it looks like. And this is another very important mistake done on the majority of designers and producers. RF transformer bandwidth. 99% of constructors, of developers, they will design for amplifier which works from 160 to 6 meters. They will design transformers to be very nicely tuned from 1.8 to 54 meg, which is a mistake, because transformer is a big door before the exit door. So if your harmonics won't pass the transformer, so they will not catch the duplexer section of the filter. So the transformer has to be broadband at least 3 times more for the third harmonic than the highest frequency. So if you have 50 meg amplifier, our transformer must be capable and broadband minimum to 150, just to allow this third harmonic to jump over to end up at the end of the transformer and then to go into the filter section. Here is, at the first moment, very nice, but disaster of transformer. So this transformer is nicely tuned from 0 to 30 meg, and then you can see the stop is on 70 megahertz, so 150. So it will be like a closed door immediately after the LDMOS for any harmonic. Not only, so it will operate for let's say, it will operate almost on complete HF, because 30 meg is 90, so the high frequencies, low bands, but 50 meg will be disaster. So actually the diplexer filter won't have any influence, because it won't receive any harmonic, because they are stopped before the transformer. Again, so, and now we have one failure by peak voltage, and we have one behavior which is a gate avalanche. A gate avalanche is a process when, because of the very strong electromagnetic field in the structure of LDMOS, it just generate a process of avalanche which is point of no return. Once it starts, you cannot do anything. So avalanche on the gate will kill 100%, and there is no medicine to stop it when it happened at the beginning. So because it's already the situation inside the structure of LDMOS is going into the damage. The only way is prevention. So you have to prevent. So the main reason for this gate avalanche are peaks, and they are happening in nanoseconds. So this is why the protection circuit must react in microseconds. Another slow but most common killer of LDMOS are thermal failure. It's not cooling which is not designed properly. So here is heatsink which is from the Power Genius. Here are Power Genius heatsinks with some testing of vapor chambers, and we find out that they are not helping much. And here is the latest heatsink from Power Genius showing the proper way of cooling. And here is one example of how it doesn't have to be done. For a couple of reasons I will explain. So here we have three materials of heatsink. So it is extruded aluminum, and their thermal coefficient is about 160. We have pure aluminum. Pure aluminum, it means they are much softer, but it's almost pure aluminum with thermal coefficient of 240 to 280, and we have copper which is 380.
And that's the copper line on the right side.
And here is the copper. So when you are simulating, modeling this thermal process, you can see on the software that as actually temperature is decreasing exponentially with the square. So you don't need it doesn't help that big piece of copper. It just helps the amplifier to be heavier. So you need a smart shape of copper or something like that, and then you need a good heatsink. So this is a good heatsink with lot of fins. Fins are very thin. You have a lot of surface, so actually you have to have a heatsink with a lot of surface, as much as possible surface for airflow, and it is how it looks like. So, but this is one of the typical. So they think if they put a huge piece of copper that they solve the problem. They solve the problem, so it's not bad. I mean, it's not worse, but it doesn't help. So it's just overweight. So the same situation of cooling you will have if you will have maybe quarter of this properly mounted below the transistors. And thermal failure is very common because the LDMOS transistors, they have one characteristic which is good and not good. Good if you handle it, but not good in exploitation, as I can see. It's the behavior that efficiency is increasing with the power. And then, for, let's say, 1.5 kilowatt transistor, you have efficiency starting from 30% on a couple hundred of watts, increasing to 75% on the maximum of the power, which is, and then it's not unhealthy for LDMOS if it is on the maximum of the output port. In opposite, it is healthy, because when you are running, when you have a fixed drain, we don't have a fixed drain voltage, but most of the amplifier they have. You have a fixed drain, and then you want to save your amplifier, its behavior coming from the time of the tubes. So you want to save, you don't want to push, but you are killing your amplifier. Why? Because on the 1 kilowatt, you are decreasing your efficiency on 40%. Let's say 50%, but usually it's 40. So it means that kilowatt is 40% of total power, and 60%, which is 1.34 kilowatts, is heating. But when you are on 1.5 kilowatt, then it's let's say 600-700 watts is heating, and 1.5 kilowatt is the output power. So with lowering the power, what are you doing? If you have a fixed drain voltage, you are dropping down efficiency, you are heating your amplifier dramatically, and you are destroying over the time LDMOSs. So another advice, if the amplifier you are looking to buy doesn't have any control of drain voltage, and it is a fixed value, forget it. So it's not good. So this is about the gate avalanche. I already explained it. This is about the efficiency one diagram. You can see 1000 watt, and we have some data, and we have 1.5 kilowatt of heating when we have 1000 watt of output power. The same voltage, we drop down voltage, we control the drain voltage. On 35, almost the same, even less amps, we have the same output power, and we have 610 watts of the heat. This is how Power Genius and what MEFA does. MEFA means maximum efficiency algorithm. So we are monitoring a drive level, and we have a function depending on the drive. When you are decreasing the power, we are changing the output voltage on the LDMOSs, keeping the efficiency always in some area where it is healthy. It's not like modulated power supply, it's much simpler, but very, very efficient. So with MEFA, you are using that on CW and single mode and single digital modes. You are always, you have a cool amplifier, no heating, and most of these thermal failure on Power Genius are because customers are not using MEFA. They simply didn't understand that. Sorry. So what will be the ideal amplifier concept? See, the output stage should have diplexer filter to root harmonics on 50 ohm. Of course, as condition, we have to have wide band transformer, which is wide at least 3 times the highest frequency to allow the harmonic transfer to the filter box. And we have to minimize voltage peaks and avalanche risk. So avalanche risk is, prevention is the only way, so we cannot stop it when it starts. And of course, everything I said is a prevention to have avalanche risk, which will definitely kill the transistor. So we have to have a variable drain. Bias control, I didn't want to go deeply now into the technical details about each and everything. So, and the protection system has to be in microsecond scale. So if the amplifier you are looking for has protection based on the microcontroller, forget it. So it cannot protect your amplifier from avalanche risk, from high peak, so it's too slow. Thermal protection with fallback, reduce power before shutdown. Now we will launch next year Power Genius version 2, and we will have the first ever thermal control, which is protection at the same time. Thermal control, which will monitor efficiency, actually, which will measure heat on the transistor, heat generated, and then based on that, we will have some protection mechanism to drop down voltage, power, whatever. So it is something which nobody is doing at the moment, but it has to be done. In our experience, last 5 years, show us some of very important ways to protect the LDMOS, and we at the beginning didn't put much attention on it, but they are very important. One of these is this thermal managing system to control your amplifier all the time. Okay, so this is analog dissipation protection. It will be independent from the software, so we have a hardware circuit which is taking care without the microcontroller and controlling the output power to make sure that dissipation, the heat on the transistor, is below some threshold we decide. Okay. And the final testing I already explained at the beginning, so our final testing is very, very rigid, and it is the only way to avoid a lot of headache with the problem after the sales. So, and this is what I already said, the way how we are testing those. So more or less that's it. I hope that you learned something. I hope you enjoyed. Things are more or less simple, but you always have to consider everything in a parallel. So fixed drain voltage, forget this amplifier. Low pass filter, forget this amplifier. Check heatsink, and check the time response of the protection. So that's more or less 3-4 basic things that everyone who wants to buy or to build his own amplifier has to have on mind. Any question? Thank you.
One question about noise. Is the power supply in standby, is it active, cooled by fans?
No, our main power supply is in standby, it's switched off. In standby, we have just auxiliary power supply for microcontroller.
Okay, that means in standby, absolutely no noise.
No. We have noise. If you go in standby and it is hot, it will cool, and at certain point it will stop.
Cool down time until it dissipates the heat, and then basically.
It is also very good. It is one of things I forgot. It's too long presentation. So the cooling and the noise. So do you think that the quiet amplifier are something you would like to have? I don't think so. Why? Because if you are running 1.5 kilowatt and you have dissipation of 700-800 watts in the best case scenario, so you have to cool your heatsink with 700-800 watts. You have to cool this. Physically, you cannot do this with quiet amplifier, quiet fan. You cannot do this. So if you have quiet amplifier, so it's again tricky, a little bit of cheating. I have a quiet amplifier. Our amplifier is very quiet when it is in a normal operation, let's say. But it becomes to be very noisy, and it saves your money and amplifier itself when it is under the very hard condition. When we have someone switched off MEFA, we have 50 volts, he put 800 watts, generating 1.6 kilowatt. You have to cool this. So the only good way is to cool this. For cooling, you have to have airflow. For airflow, you have to have noise. So it's simple. So noisy amplifier is much better than these quiet amplifiers. Water cooling is a solution. Technically, of course, it's the best solution. Quiet, more efficient than air cooling, but commercially, it's very tricky. So we have our water-cooled amplifiers. They are working perfectly, but we decided not to launch this model because we will be called, or support will be called a million times by customers because it's not easy to handle. And, you know, we have customers, they are not technicians. I want to buy amplifier, I don't want to take care about putting liquid into the cooling system. So this is practical reason why we don't want to launch water-cooled amplifier.
Do you design these amplifiers for commercial using only, or additional for commercial using?
Yeah, we have now 10 kilowatt models for whole HF up to, for any frequencies up to 50, 60 megahertz.
Is it like the same practice like here on this presentation?
The same practice, yes. Principles are the same. Yeah, without some compromise. But in Power Genius, we didn't make any compromise. For example, I said that the filter box is the most important. Indeed. So when we are designing filter box, first, the quality of components are military grade. We are not buying military capacitor, but commercial grade. So, and then we are buying those most common, you all know, ATC 100C models. We are buying from another military company. And when we are designing filter, we have our software. We are calculating the currents and the voltage on every point in the filter. And then we are generating, through the MATLAB, we are generating and finding a worst case for the current with load 1 to 3 over the Schmidt. So depending on the nature of reactance, the current for the same SWR is varying. So we are finding the worst case, the maximum of the current, and then we are putting capacitors capable to survive 1 to 3 into the worst case scenario. And this is how the filters are designed and produced in Power Genius. And we really have almost zero failure in the filter boxes, because capacitors are such a good quality. Nominal current is whatever it is, but they will survive double of this current. So when we calculate 1 to 3, it means that it's really. And also you can see the quality. Amplifiers, it's very, very wide scope of little but very important things in designing this. Any other questions? No.
But it's possible to look into equipment downstairs.
Absolutely, we can open one, of course, and we will open one. No problem. And fan is also very tricky. I like this question, so it's also more noisy. It's better. Because technically it has to be done. You have to cool your amplifier. So if someone is trying to sell you the amplifier, saying, "Oh, it's very quiet, you know, Power Genius is very noisy," but you see it. So it's just a bullshit, because the lifetime of LDMOS depends on the working temperature, operating temperature. Lower temperature, lifetime is longer. Very, very simple. Thank you very much. We also have some topics we planned today. I don't know if we have a time. If you want, we can go through the subject which I am calling Lego, or how important is to design hardware in a way to be upgradable and to be a Lego of our ecosystem.
Sorry, question about this. The aberration of LD-MOS. Can you explain that?
Sorry?
The aberration of LD-MOS. The aberration, yes.
Abbreviation?
Yes. LD. What means LD? Low drive or?
No, it's
lateral diffuse.
MOSFET transistors. No, it doesn't have anything with the drive. No.
Can't explain it.
I think it means lateral diffuse.
Yes. You're right.
So we will look outside the practice.
Yeah. So